Yeah, I have always enjoyed being here. So today I'll be talking on BMS3 and invariant dual field theories. As I'll go on, I'll tell you what these quantities are. Probably some of you know and probably some of you do not know. So anyway, we'll go ahead and see. And I'm sorry that I won't be able to give, I'll try to give backgrounds as much as possible, but since like I do not have that much of time, I won't be able to give too many details, but you are free, just feel free to stop me if any point you think like it's not clear, okay? So let's go ahead. So the plan of the talk is following. I'll first tell you what is BMS and why the 3, okay? Why we are doing 3 dimensions. This 3 has to do with the dimensions of space-time, and I'll tell you why 3D. Then I'll tell you about BMS3, this symmetry algebra and its supersymmetric extensions. In particular, like they are asymptotic symmetries of 3-dimensional supergravity theories. What are they? How can one get these symmetries? How can the various possible ways to get to the symmetry algebras? And then once we have the symmetry algebras, then what we can say about the solutions of the gravity theories, and then whatever we can obtain after this much of analysis. And then I'll go this part. I'll try to I'll do it in a hurry, but anyway, again stop me if something is not clear. Here I'll talk about the dual field theories to 3D gravity. I'll explain in what sense they are dual, and they would be like Weizmann like theories, or even we would be able to understand them as some Liouville theories.
And so 3D gravity is in flat space,
right?
But you're saying that there is a duality.
Right. So I'll tell you exactly in what sense. Okay, yes, 3D gravity in flat space, right. So let's go ahead. So what is BMS? So as we know that this symmetry algebra at null infinity for gravity theories with flat space asymptotics are known as Bondi, van der Burg, Meissner and Sart's algebra, and that is what is BMS algebra. So don't get into the name. What we are basically trying to understand is we have gravity theory of Einstein's theory, and such that we are only interested in such a theory whose asymptotics are which are asymptotically flat. Okay. In such a scenario, if you are going to the asymptotics of your space-time, what is the symmetry? We all know that in the bulk the symmetry is just Poincare. The question is, if when we are going to the asymptotics, is it still Poincare or something else? So that's what we are trying to understand, and that as it turns out, the answer is no, it's not just Poincare, it is more than that, and that symmetry algebra is known as BMS algebra. So in 3 and 4 space-time dimensions, this algebra, the BMS algebra, is actually an infinite dimensional algebra, and they contain infinite number of generators which are known as super translation generators and super rotation generators. So these are, this super has nothing to do with supersymmetry, this is just a name. Okay? And in higher than 4 dimension, so the algebra is not exactly, it is not super translation and super rotation both. In fact, you can show like with certain relaxation on the boundary conditions, one still gets super translations, but super rotation is not there. So it's only super translation plus Lorentz transformations as the asymptotic symmetry generators that you get when you go to higher than 4 dimensions. In fact, only for even space-time dimensions. So far in this talk, we will be only interested in asymptotically flat gravity in 3 space-time dimensions. So I'll not be talking about 4 space-time dimensions, although that's very, very interesting, and the asymptotic symmetries in 4 space-times have important implications. But in this talk, I'll be only talking about 3 dimensions. So that suddenly brings me to the question like why 3D? So 3D is for following reasons. First of all, gravity in 3D is special because there is no dynamical graviton. So like you might think then why it is special? It is special because even if when there is no dynamical graviton, there actually exist a large number of solutions whenever the global topological structures of your space-time is non-trivial. By that I mean if your global topology is such that you have some non-contractible cycles in your space, then the solution is not really trivially Minkowski. Of course, at every locally all the solutions when you are in asymptotically flat space is Minkowski, but when you are looking at the solution from the global perspective, they won't be. So that is why you have large number of solutions in your system, and on moreover 3D gravity is also is a renormalizable theory, and thus is a perfect toy model to study some quantum aspects of gravity. So, what I will be doing is we shall be using Chern-Simons formulations of 3D gravity to study the asymptotic properties of the theory, and also we will see that it will give us as bonus some other interesting aspects of the theory as well. Okay, so that is what we will be doing. Is there any questions at this point? This is like more or less a plan. If not, so then let me go ahead.
You are going to be interested in quantum aspects?
Yeah, eventually yes, but in this talk I'll tell you like how far we know, but not I mean I would not comment much about the quantum aspects because we still do not know much about it, but I'll tell you like how far we have been able to understand. Okay. So let me first tell you very roughly like how do we get asymptotic symmetry algebra. Okay. So although I will be using Chern-Simons formulation, but before I do that, let me tell you like how if we are given a space time, like any space time, for example, for any space time, and we want to go to its asymptotic region, and we want to understand that what is the symmetry there. Okay, so if this is the question, how does one proceed to understand this, to answer this question? So to do this, one should actually work in the Penrose compactification, and one should really like to analyze this at scri plus or scri minus, which are the null infinities, future null infinity and past null infinities, because there the expansions in 1 over r is smooth. So these are the best possible regions to address these questions, and that is what we will be doing. So, yeah, right, sorry, yeah. So here, although whatever I am going to talk about in the bulk of the talk is for 3D gravity, but this slide is generic. Okay, although I have written for 3D gravity, but whatever I will be saying later on is applicable for any theory. So what we have to do for understanding or answering a question like this is following. You first find out a metric solution with proper fall-off that describes the geometry of an asymptotically flat manifold. So by that I mean say any theory, I mean let us just take this, let us just say that any d-dimensional theory R, okay, you write down the equation of motion which is nothing but GAB equal to TAB. Okay, TAB is for some whenever you have some point source in general. So if you do not have it, then this is 0. So what we are trying to understand is what kind of solutions that we can have such that when we will go to the infinite limit, then this will boil down to eta mu. Okay. But I must tell you that this does not mean that G mu nu at r goes to infinity is strictly eta mu nu. It is not. It is not. So we'll have to find out the proper fall-off condition on my solution such that when we are going to the infinity, it is still eta mu nu. Okay? And this is a very, very important step to do at the very beginning. So
this is part of rules of quantum gravity. I mean, how to figure out
right.
what are these boundary conditions,
Right.
and what determines these rules.
How do you find it? So the way one needs to do it is basically again we need to find the solution of these equations such that whenever there is a point source and you are going to the infinity, at infinity the effect of the point source is 0. That is the demand that we have to make. So there can be a point source. So in the bulk the solution is very non-trivial.
No. So when you are talking about solutions, I understand. Because that's some solution.
Right.
But quantum gravity is
you are talking
over
no.
non-solutions.
Right. No. So at this step when you are trying to understand the asymptotic symmetries, this is still at the level of solutions. Okay.
You can ask more generally that what are the boundary conditions that are allowed by asking
right.
that your charges are finite. That's it.
Right. And here the corresponding statement would be that when you are at large r, when you are at asymptotic infinity, the effect of all the all the mass sources are negligible. So to what order that should happen, and that is what will give you the proper boundary conditions on G mu nu. So one has to start with that, and then the next step comes where we
Sorry,
yes.
I got something. So the 1 over r
Right, right.
But here it should be log r.
No, no, no. No. So,
Flat space.
right. So, like some of the terms will be, so I can write down the metric. So, basically this is again, I am just writing flat Minkowski metric. This you can write it as minus dr square plus du square du dr plus r square d omega square. This is just the flat space metric, but this is, I mean, this is nothing but eta mu nu. This is nothing but eta mu nu dx mu dx nu. But then the right fall off is following. So there you write it as minus exponential of some Vr du square plus some other functions. I can write it as Fr du dr plus some gr r square d omega square. And by demanding that this solves the equations of motion, one has to find the fall-off conditions on various quantities.
And
it won't be. So, for example, Vr would be 1 plus some 1 over r kind of term, plus 1 over r square kind of term. This kind of things are allowed. So, one can show that even when the fall-offs are like this, the space-time is will still satisfy this property, that when you will go to large r, it would be
it doesn't go like the Green's function. I mean, in 3 plus 1 dimension, I know that h mu nu was 1 upon r, but in 2 plus 1 dimension,
Maybe I can make a comment. This may or may not be right.
Yeah.
But, the two things that come together in 3 plus 1 dimensions are coincidentally the same. The first is that the potential that saturates Coulomb law, the static Coulomb law, is 1 by r.
right.
And the second is that the radiation fields, such that their square gives finite energy, is
Right.
also 1 by r. And this is a coincidence in 4 dimensions. So, for instance, the radiation field here, I think, would be 1 by square root r.
right,
And since we're looking at psi plus and psi minus, the Coulomb thing is not so relevant.
right, right. So,
Radiation thing.
right. So, but the similar thing can actually also be done in 4 dimensions. So, if I want, so although I mean we are interested here in 3-dimensional gravity, but this asymptotic analysis can also be done in 4 dimensions, and there also it goes as some of the terms goes as 1 over r and some of the terms goes as 1 over r square. There is no log term.
So in odd dimensions, let's say if you have a scalar field, then that has some specific properties for propagation. Here also you will have some signatures if you do odd dimensional. I mean, is there a way?
So, right now it's just pure gravity.
Right. So instead of say if you have a Minkowski space and a scalar propagating,
Mm-hmm.
you are calculating Green's functions.
Mhm.
That is very distinct difference between even and odd dimensions.
Right.
So if you want to calculate the fall-off conditions for the scalar at you go to pi plus or pi minus, that will be different because
Right.
of this property.
Right, right,
So I'm asking that in this case, this is like strictly like gravitons in this case.
right, right.
You have that distinction. Oh, in the previous slide, why did you say that I am restricting to only even dimensions?
No, 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 no. I didn't say that. I didn't say that I am restricting to even. I said that in higher than 4 dimensions, when the space-time dimensions are even, then also the asymptotic symmetries is well understood. I mean, like we can really understand it as the super translations and whatever is the kind of generators that we have, but not the infinite dimensional super rotation. So, okay, maybe these nomenclatures are not very clear. So, let me just tell you what is super translation and what is super rotation. So, like when you are going to, let's again take, so let's take this only. ds square is like du square plus some du dr plus some r square d omega square. So, when you are going to r goes to infinity limit, basically your space time now consists of u and this one direction phi. Okay. So, super rotation is like just motion, I mean just the diffeomorphism of the circle. Super, yes, here I mean in 3 dimension it is just a circle, in 4 dimension it is a sphere, right. But in super translation is when you are translating along u, but that translation is itself a function of, that transformation is a function of phi also. So, this kind of a transformation, which is really like a translation because it's you are really changing the u direction, the time like direction, but the translation, the transformation is a function of phi as well. So, that those are like super translations. What I am trying to say here is when you go to higher than 4 dimensions, then at least for even space time dimension, this is well understood that you will still have the super translation, and only this infinite dimensional super rotation symmetry is certainly not there. Instead of that, you only has Lorentzian.
But what is the distinction? Like here, how do you see that there is something circular over all dimensions, just roughly at least at the level of equations?
No, I mean it is not even that. I mean most importantly, like that you do not have an infinite dimensional extension there. That's is more important, because here like you have for a circle it can be any function of phi that can give you the symmetry. Even when you have S2, it's basically the entire conformal symmetry of S2 that you can have. That is giving rise to super rotation generators. But when you are going to higher dimensions, then that is not true. I mean that the symmetry of higher S's are like finite dimensionals, and that's what will make this space to be finite dimensionals. Okay, so
apart from it being finite dimensional,
Right.
dimensional, do you have additional subtleties in understanding asymptotic symmetries or let's say soft theorems for gravity?
See, soft theorem will exist. Let us not bring, I mean, I know that asymptotic symmetries are interesting because there is a supposed relation with the soft theorem, but soft theorem is a separate statement and asymptotic symmetries are separate statements. Okay. Now, in 4 dimensions, of course, one can see that soft theorems comes from the word identities of asymptotic symmetries. In higher dimensions, what again in higher even dimensions, what Strominger claimed is that for only the super translation word identities are still there, and the part of soft theorem that can be understood at the word identity of super translation generators is intact, but other part is not. Okay. But that no way means that we do not have soft theorem. Soft theorem we have. Okay. So, let me go ahead. So, this is the first step, and the next step is so this is the fall-off conditions that we first need to understand, and then to understand what is the symmetry of that space-time, what we do is following. So, we look for the isometries that leave this asymptotic fall-off behavior of the metric invariant. So, whatever be those isometries, those killing vector fields actually generate a symmetry algebra at the asymptotics, and that is what is basically the asymptotic symmetry of any space time. Okay. Now, if instead of just gravity, if you have certain other matter coupling, then you need to do the same thing for all other matter fields. We need to find the proper fall-off conditions for other matter fields, and we need to understand like what should be the symmetry directions, the diffeomorphism directions and other possible symmetry directions that will not change those fall-off, and that will eventually give you the symmetry algebra at asymptotics. Okay. So, this is the generic procedure, and one can actually apply this to understand the asymptotic symmetries of gravity in flat or ADS space in 3 or higher dimensions, and people have done it. But as it turns out that this is pretty non-trivial to do when you have matter couplings to the system. So, whereas the implementation of the same criteria is much easier in the Chern-Simons formulation of 3D gravity. But this is only true in 3D because we have only in 3D we have this alternate formulation of gravity. So, we cannot apply the same tricks to understand asymptotic symmetries in higher dimensional gravity. So, that is it. So, let me go ahead. So, now I will try to tell you very briefly what Chern-Simons formulation is and how it is, how that formulation can actually be thought of equivalent to 3D gravity. Here probably all of you know this much better than me, and anyway I will be only talking about classical Chern-Simons theory, pure Chern-Simons theory, and the action is just given by this. So, here K is a parameter, so far for me is just a parameter of the theory, and M is a space-time 3-dimensional space-time manifold on which the theory is defined. A is a Lie algebra valued one form. So, A can be actually expanded in the generators of the Lie algebra like this, and this quantity that I have here basically represent the non-degenerate invariant bilinear form that takes the value in the Lie algebra space. Basically, you can think about this quantity giving me the metric in the Lie algebra space. So, once we put it back here from the knowledge of the algebra, one can explicitly write down this action and can see how the full thing would look like. The equation of motion for this system is very simple, and it is just F is 0, and from here it is even easier to understand that this theory does not have any non-trivial dynamical degree of freedom. It is a completely topological theory, and hence all other solutions that you have are pure gauge, where G is any Lie algebra group element, and one can choose a gauge fixing condition. For example, in radial gauge condition, the solution will just look like this. Okay. Now, let us just spend a minute here to understand the solutions. So, the R component of the gauge field is given by a completely arbitrary function BR in this form. The A phi and AR involves BR as well as these two quantities A and B. These are functions of U and phi. Okay. So, the interesting fact of this answer is following. So, I said that there is no dynamical degree of freedom and the solutions are pure gauge. But here what we can see that even after fixing the gauge condition, the solutions are not completely fixed. They are fixed up to these unknown functions. So, they can be any functions. Okay. In particular, A and B represents the residual part of the gauge field, and that just by choosing a gauge fixing condition cannot be fixed. So, these parts, these freedoms we still have, and they will actually give the residual gauge freedom of the theory, and the conserved charges that corresponds to this residual part of the gauge symmetry will actually produce the entire centrally extended symmetry algebra at the boundary. Okay. So, again I am just telling you like from where one can get the boundary algebra. It's of course not very trivial to do that, but it is at least at the level of understanding it is not that difficult either. So, if you have any question at this level, you can stop me.
You will need boundary conditions for this A and B.
Yes, right. I'll exactly. Okay, so let me go ahead. So now, so this is just pure Chern-Simons. Okay. Now let me tell you how pure Chern-Simon is also equal to 3D gravity. Now for 3D gravity, we know that this is also a topological theory because it does not have any bulk degree of freedom. The symmetry algebra here is just the Poincare algebra, the Lorentzian translation, and the group is IISER 2,1, and this is a non-compact gauge group. Okay, that's the only non-triviality about it. And the non-zero commutators of the corresponding Lie algebra is this, where J is just the rotation, the Lorentz transformations, and P is this translation. So it is simple. Now what we can do is we can again get back to our Chern-Simon theory, expand A in the generators of IISER 2,1 and compute the metric in the Lie algebra space of IISER 2,1. Once you do that and then you evaluate the same Chern-Simon action, you actually straight away get this. Okay. Same, here I have done it for asymptotically flat gravity. You can as well do it for asymptotically ADS or asymptotically DS gravity. Only difference is the gauge group changes. For asymptotically ADS it is SO 2,2, and for asymptotically DS it is like SO 3,1. So that's the only difference. But with that and with the properly constructed the invariant bilinears, one can get all 3D gravity starting from Chern-Simons.
So this gauge group is not some local. It's not some. It doesn't have to do with the just the.
This is just Poincare symmetry of my theory.
That is because the asymptotic thing is Poincare.
No. I mean even the bulk symmetry is Poincare. No, in 3D gravity the bulk asymptotic is not Poincare, but the bulk symmetry group is Poincare. Okay. So all I'm.
What did you say about it being different in different cases?
Oh, okay. So what I'm saying is so the Chern-Simon theory is this. Okay. Yeah. It is defined for any Lie algebraic valued one form. The group can be anything, and all you need is a 3 manifold on which you are defining your theory and the gauge group, and for me this is at the classical level. For me K is just a parameter. That is what is Chern-Simons, classical Chern-Simons. Now if I choose this gauge group to be this, yeah, and expand my gauge field in the generators, use the corresponding metric in the algebra space, then the same action would just look like this. Okay. Where R is nothing but, so this is like the VLBNs and these are like the spin connections. So I will get this. But instead of choosing this, if I would have chosen SO 2,2, yeah, I would have gotten an extra term here, which is the cosmological constant term. If I would have chosen this to be SO 3,1, I would have again gotten a cosmological constant term, but with opposite signatures. So that's how from Chern-Simon one can actually get all 3D gravities. So just small difference in the, of course the symmetry groups are different, and that's what one has to take into account. Of course, one needs to, just a second. Of course, one needs to further identify this constant k with 1 over 4g to get it, and the manifold on which we were defining the Chern-Simons theory should be taken as R some time direction times a compact space sigma. Yes.
So, sorry, this may be a very dumb question. But
No, no.
The gauge group for the Chern-Simons is now compact.
Right.
Is there a problem with like the bilinear form not being possible?
No. Very good question. So, this gauge group, until unless I can really construct invariant non-degenerate bilinear forms, these are not useful. I mean, I cannot write down the corresponding theory in terms of the basic fields. Okay. So, even though the gauge group is non-compact, you can find it.
There is no problem with like the kinetic terms being.
No, you can no. In the field space, the metric is defined, well defined, and is non-degenerate. Both are important, and then you can like get it. Okay.
So the number of generators here is, I mean, the gauge group is some complex version of SU2 in this case, right? SO3.
Right.
Whereas in the ADS case, it was some complex version of SO4.
Right.
So it's much smaller gauge.
Right.
This
Yes.
is not compact. Sorry, this is not non-compact version of SO3. There is an I also. It's an I. It's a translation.
Yeah. Barring translation, yes. With translation, it is this. Yeah.
Comma and R.
Okay, thank you.
The
Yeah.
J's are the SO2 comma.
Yeah. J's are the rotations.
So
Yes.
3 translations and 3.
3 rotations. Yes. Yes. And yeah. No. Go ahead.
A equals 0 is the solution, right? What does that correspond?
What?
A equals 0. Mu equals 0. Something that you can make sense of in Chern-Simons theory.
This would trivially mean that e's and omegas are all zeros.
So that's a very singular thing.
I have to think about it. No. Okay. Yeah. I must tell you that at this level, when I am talking about that the two theories are equivalent, these are just classical equivalence. All that by that, your question is still there very much, because that's just a classical solution.
First
But
paragraph
that would
of
mean-
Newton's paper says that A equal to 0 would be something great to make sense of. Because it might come, correspond to
Something what makes sense of?
This A equal to 0.
Yeah. What was the?
Corresponds to G mu equal to 0 rather than G
Yeah.
mu equal to eta.
Eta mu nu, right? Yeah.
So he leaves it hanging. He says that the G mu equal to 0.
Hmm.
Could it mean some different kind of completely symmetry restored phase or something? And G mu equal to eta mu could be some symmetry ringing or some big theorems. Just to say,
Okay.
some statement made.
Certainly one cannot get rid of it by, I mean, one cannot get to that phase by choosing some gauge, no. But how? I mean, here all the solutions are pure gauge. So that would mean that in Chern-Simons all solutions are pure gauge. So that would mean that from one solution to other solution, one should be able to go by gauge transformations.
It could be different class of free gauge solutions.
I'm sure boundary conditions will play an important role.
Yeah,
For instance, for asymptotically ADS spaces,
Yeah.
you want to put the condition it's asymptotically ADS.
right.
That will not be available.
Yeah, even here that is true. One has to put the proper boundary conditions on sigma. Yeah, that's true. Yeah, I mean, 3D gravity is a special Chern-Simons theory with this gauge group, yeah, and with the manifold being chosen as this, right? Okay, so
It's a question about quantum thing. If you
Probably.
want to include this space in that particular.
right.
Even classically in your phase space, your phase space is defined by some boundary conditions.
Yeah. So then A equals 0, as you said, doesn't make sense. But I'm saying it's still a question quantum mechanics.
Quantum mechanics. So what is your quantum mechanics defined?
Right. Okay. So at this level, all that we have seen is that the two actions are equivalent. One can go from one to other, but this the equivalence between the two theories is true even at the level of classical symmetries. So, the classical symmetries are also identical. In particular, one can show that on shell the gauge transformations of Chern-Simons theory is identical to local Lorentz transformations and diffeomorphism transformations of 3D gravity. This statement is again plays a very important role when we will try to find the solutions of this theory, various solutions of this theory. And the residual boundary symmetry of CS theory will identically then imply that there are some sort of residual symmetry in the corresponding gravity theory as well, and one can then try to construct the asymptotic symmetry algebra of the corresponding charges. And that is how one can do it in the using the CS formulation. It is much simple, and the symmetry algebra just looks like this, where J's are the super translation generators and P's corresponds to super rotation generators. So, this is the asymptotic symmetry of 3-dimensional pure gravity. Here you can see that these are like these m's and n can run over any possible values. So, this is an infinite dimensional symmetry. Of course, when you take m and n to be -1, 0 and 1, this just gives you the bulk ISO 2, 1. So, what I am trying to say is your asymptotic symmetry, your global symmetry is very much a subgroup of the asymptotic symmetry, and but the asymptotic symmetry is much more than that. So, when you are doing gravity theory in the bulk, you just have finite dimensional symmetry, but when you are going to the boundary, you are getting infinite dimensional symmetry enhancement. So, that is it.
But I mean, at least normally when you look at Chern-Simons theories with a boundary, you need to be careful about defining a boundary.
Right.
Have you?
Yes.
Have you told us about that?
Yes, yes. That is very, very important to get to this point. Yes.
If you are doing this computation not in 2+1 but in 4+1, then I believe there will be additional problems of defining boundary conditions because of the same thing that I was saying, that in the bulk you will have propagating gravitons, and because of that the fact that you are in odd dimensions and their propagation will also have, they will not be confined on the null surface.
Right, true.
Those additional complications are not there
In 3 dimension, right.
That will make this analysis at least some amount of simpler compared to 4+1.
Right. I mean, I do not think so far anyone has studied asymptotic symmetries of 4+1 dimensional gravity using Chern-Simons. Although, like the
Any ways of doing that.
Right, it would be right. I mean, you have to take those things into account when you will do this. Right, true. Yeah, there is a C1, just wait for some time. Yeah. For the time being, you can just think of it as C. All I am trying to say is that this particular one is centrally extended for pure gravity, this one is not. Okay, so let us go ahead. So asymptotic symmetries of gravity theory from CS. So what I have roughly tried to tell you is following, that CS formulation of gravity is useful to understand various properties of 3D gravity. And this was of course first established by Witten and later rigorously used by Hainaut and collaborators, but mostly in the context of asymptotically ADS gravity. So, for ADS3, I mean Hainaut probably did whatever he can do using the Chern-Simons formulation. I mean, by that I mean understanding the asymptotic symmetries, understanding the BTZ solution, understanding its thermodynamics, the corresponding states and everything was basically done by using this formulation. But what Banerjee did basically in the past decade was he used the same tool for understanding the asymptotic properties of pure gravity as centrally extended BMS symmetry, and this is when like these are flat. Okay, so Banerjee basically used, he started using the same trick for understanding the properties of flat gravity, and this technique is highly successful, and I will try to explain it in a bit detail more in the later transparencies. And by using this, by now we basically understand all possible supersymmetric extensions and even higher spin extensions of BMS3 algebra. So, yeah, so let me go ahead. But before I tell you exactly how these things works in CS, let me tell you that there is an alternate way to get the algebra, particularly the 3-dimensional asymptotic symmetry algebra, and that is by taking the flat limit of ADS3 asymptotic algebra. So, you can start with 2 copies of Virasoro algebras. I have denoted them by L plus and L minus, and C plus and C minus are the corresponding central charges, and then you just redefine generators and central charges as this. So, this is kind of taking a combination of the original generators and multiplying it by a small parameter epsilon, which is related to the inverse length of the ADS, inverse radius of the ADS, and then take the radius of the ADS goes to infinity limit, which effectively means taking epsilon to 0 limit. And similarly, you can define these two C's from the original central charges of the theory, and this contraction, which is mostly known as Inono-Wigner contraction, gives you a contracted algebra which looks like this. So, this is where you see that you also get a C1. So, even this algebra may become centrally extended. So, they get cancelled. Like in J so this in J there is no epsilon. So, when I redefine these generators, I redefined it in such a way that when I will take epsilon goes to 0 limit, the algebra should be well defined, nothing should diverge. And the proper redefinition turns out to be this, that you need to multiply this combination with an epsilon and say that in the epsilon goes to 0 limit, this entire combination is finite, whereas in the epsilon goes to 0 limit, just the 2 subtraction is finite. So, these are finite generators.
So, in BMS3 you will have soft modes.
Yes.
And can you identify the analogous soft modes in ADS3, which in flat space limit will go to those soft modes?
I think so, yes.
And, okay, so you will come to that, right?
No, I will not, because not in this talk, because I will not at all use this technique to get BMS. I will tell you why.
That is interesting, because in ADS3, what are the soft modes? Is there anything universal about them to understand that? Something that at least in flat space limit has some universal behavior.
Right. So, like some, so I'll tell you. Okay. I mean, I'll not tell you in his language, but I'll tell you what those modes are in the in direct gravity language.
In BMS3 you will tell.
Yes.
But won't it be just some modes whose wavelength is kept to the size of ADS?
Right.
And
And then go take the go radius
Is
goes
there
to
anything
infinity.
Universal. Maybe once I identify them.
Before, after, in the limit. Before the limit, they're just normal.
Yeah.
When you take the limit, they are very spacer. So is there
Right.
anything that you can say in 1 by R expansion, let's say, 1 by length of the ADS expansion?
What is this epsilon doing in terms of the geometry of the ADS?
It's proportional to the inverse of ADS radius. The epsilon is proportional to inverse of ADS radius. Okay. Now, but now let me tell you one thing. So, this was like really an extremely nice way to look at BMS, and not just that, this algebra is also identical to the Galilean conformal algebra. So, at that point people thought that BMS and GCA are probably same, the two theories, that the two symmetries are identical and there is a correspondence between the two. But that is not quite correct. Okay. So, the reason is, so here there is just one possible way to take this limit in finitely, so that one gets a meaningful algebra. But when one adds more data to the system, I mean when one looks at not just pure gravity, but pure gravity with higher spin fields included, pure gravity with some supersymmetric fields included, then it turns out that there are multiple ways to take this limit to consider this Inono-Wigner contraction such that the resultant algebra is meaningful. When I say a resultant algebra is meaningful, by that I mean it is finite, it satisfies Jacobi identity, and it satisfies the properties that an algebra should have. So, from an algebra perspective, there is no way to say like which algebra one should consider and which algebra one should not. In fact, all of them are valid algebras. But this is not enough for us to conclude that these are the symmetry, asymptotic symmetry algebras of the certain gravity theories that we are interested in.
In flat space, limit will dictate what to do, right?
No. So, that is what I am trying. So, you can, so what do I mean by flat space limit? By that I mean I am just taking various combination of these generators and then I am multiplying it by a by this parameter epsilon and taking the limit epsilon goes to 0. Now, you can do it in multiple ways.
What's the general thing though, because what you want to do is you want to introduce a parameter of dimension 1 over r.
Right, absolutely.
Then it needs to be taken.
I will show you that as soon as you have other generators, you can do it in multiple ways. Okay, you can scale certain number of generators and may not scale other generators at all, that you have seen already here. I have only scaled P with epsilon.
Dimensional analysis I am saying. So
Yes.
A is the dimensionless.
Right. But when you will have supercharges, like they both different kind of supercharges, I can decide to scale one class of supercharges and not the other class of supercharges. They are all supercharges, so dimensionally same. And then you can even consider like I will take combination of supercharges and scale them, or I will not take combination of supercharges at all and scale them. So one can do it in multiple possible ways, and then one does get consistent algebra that satisfies the Jacobi identities and things like that. But that's not good enough for us to conclude that these are the symmetry algebras of gravity, asymptotically flat gravity theories coupled to suitable matter content. Okay. So that.
There is no canonical way of. So the thing that we really want to do is to take the radius of ADS to infinity, let's say.
Right.
That does not naturally say that some coordinate has to be scaled somewhere, so that some charges has to be scaled in an natural way. There is no natural.
There is. So there is. But what you are asking is again, basically you are trying to understand flat gravity as a limit of ADS gravity, right? So if you do that, then there is, out of all these possible ways, only one will be favored. Okay? But if you just do it directly from the algebra, then you cannot say. That's what I am trying to say. Okay? So, but this was like the most easy thing to do, and people thought that it would work, and in fact, I mean, we also wrote down all possible supersymmetric extensions of BMS based on these criteria. Okay, so that's what I just want to say, that in these papers, like me with Sunil and his students and Dilip in Pune, we actually constructed all possible supersymmetric extensions of BMS3 along with their free field realizations. I mean, we also said like how just as free field theory we can understand this system. I mean, what free field theory will have, what free field theory, yes, I want to stress on that, will have BMS3 or its supersymmetric extensions as the realization of its symmetry. Okay, so that also we could do, but what we at that point what we understood is that there are.
You want them to be strictly free.
Yes, I wanted them to be strictly free, and I could get it. Please keep this point in mind. I'll come to it towards the, I mean, at the end of my talk.
Sorry, but you almost suggest you want free field realization.
Yes, I wanted to see.
You want to see if you can. Like,
Yes, exactly. I wanted to see if I can write a free field realization of that, and then we were successful.
It's not a limit. You sound like, I mean, you're talking about it like it's a limitation that it's a free field realization.
No, not at all. So what I wanted to say is I first constructed the symmetry algebra, and then I wanted to see if there is a free field realization possible for this, and we were successful in getting that. Okay? But then what we understood here itself is when you have supersymmetries and higher spins, there are distinct ways to take the limit, and all corresponds to valid two-dimensional algebras. This is what I was trying to say. And in fact, you can impose unitarity constraint to put certain restrictions on this algebra, but even then, even after imposing unitarity constraints, you could get two distinct algebras where both of them satisfy unitarity bounds and they are different from each other. Okay? So there was no unique way to pick up like which algebra would correspond to asymptotically flat gravity. So thus, I would say at this level that thus a direct asymptotic symmetry analysis of the corresponding supergravity theory was very much required to identify like which of these algebras that we were getting corresponds to the symmetry of exactly which theory. Okay? And that is what we then performed. So this calculation was only possible in like in Chance-Simon formulation. So we performed that in these multiple papers, and we have then we actually understood that how to make sense of all the symmetry algebras that we found, and like which of them would correspond to the asymptotic symmetries of flat, I mean asymptotic symmetries of 3D supergravities when you have, or asymptotic symmetries of higher spin supergravity theories, higher spin gravity theories, and then like how one can actually understand it from taking the limit of ADS supergravity theories. So that also one can.
So can I see one thing?
Yes.
Probably something very basic. So from ADS to flat space, when you want to go, you want to take the limit where the conformal dimensions of all operators go to infinity.
Mm-hmm.
Because as the radius of ADS goes to infinity, you want to keep the mass fixed. You want
Right.
to take that limit.
Right.
And that is not some canonical thing.
Right. Right.
This even if you do this, there are many other things.
Right.
To play with.
Right. Right.
Yeah,
So
dimensions are at the level of let's say the specific theorem.
no, but the generic statement should be true for all. So here I can roughly tell you like what one has to do. One needs to take 2 copies of asymptotically ADS gravity and then consider their right combination so that you can get the flat gravity out of it. So if you do that even at the level of all these boundary fields, the A field and B field that I was talking about, and impose the same conditions on their follow-up, then you can actually get to the results of the asymptotically flat space that you would have. But yes, like that's.
Dimensions large, let's say, it corresponds to what in this generator language, what you use
But that would.
are parametrically small or quasi
No, 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 it doesn't.
Is it a standard?
So, okay. So, any questions so far? So now let me tell you like how this calculation really works. This is what Shiraz was asking me, and I will do that. Okay, I mean I'm going to present it for n equal to 2 comma 0 supergravity, but for understanding you can actually just forget about the supercharges because the understanding is same. Or if you want to see, I mean I have turned on the supercharges and also the R charge gauge fields because that brings the non-trivialities to the system, but at the level of understanding it's same. Okay, so here the algebra that the basic algebra that one should start with is in 2 comma 0 super Poincare algebra, and the generators are following. The non-degenerate bilinears you can compute for this system, and these are this. Here you can notice that I have two arbitrary parameters, and those are allowed. So far you are only interested in computing the non-degenerate bilinears. So one doesn't need to set them to any specific values. For any arbitrary value of them one can get the invariant metric. So I have kept them arbitrary at this level. And then what I need to do is we need to expand the gauge field in this, and then write down the corresponding, from the corresponding chance-Hammond action we can get this gravity action. So here it is really gravity, it is supergravity, and that is coupled to some R charge gauge fields. That is what the theory is. So gravity and coupled to scalars and coupled to the gravity now. And in
One residue means
sure.
if you restrict to the global part of the conformal algebra,
Right.
just the global, not global, then that goes to some nice subgroup for the
Right.
asymptotic part.
Right. So, global part of what algebra? Sorry.
Conformal.
I mean the global part of your entire bulk algebra is a sub-algebra of the asymptotic algebra.
Sorry. In ADS3 you had this conformal symmetries on the boundary.
Right.
Now just restrict to the global part.
Right.
Don't take the whole reaction. Huh?
That's ISO 2,1.
Yeah.
That's what the
Here.
algebra,
Yeah.
denominator is.
Yes.
Okay.
Yes, but I just wanted to understand the global part of that.
That's the global
the
part.
consistent. Yes, this is the global part. So what does it go to in the other sector? Does it also go to some?
Poincare symmetry.
And my question is because maybe.
But what I am trying to say is this entire Poincare symmetry would be a subgroup of your asymptotic algebra.
Definitely.
Yes.
That will be there.
So that is what did put the unitarity constraint on my theory. From that only I got that certain commutator has to satisfy certain properties, and even after imposing that we could get multiple algebras.
Sort of like in the sense that the global part was the isometry space of ADS,
Right.
and the flat space limit becomes the isometry space of
Yes, the
Absolutely.
only question that I had here is
Hmm.
to understand, not just that, but how does translation work in this picture? But I'll ask later.
I'll tell you.
Because that is non-compact.
She had it in the epsilon of one of the L minus
Yeah.
L bar had an epsilon.
Right.
No, the L plus L bar.
Didn't. Yeah.
That was
That was the translation, right?
Right.
So this is the non-trivial.
Yeah. Right.
I'll ask.
Okay. So okay. Now here I am coming to Shiraz's question. So next what we want to do is we want to first write down the solutions for this theory, and as we have seen that this is pure gauge, and even after fixing a gauge fixing condition, we cannot fix this gauge field completely. So what remains there is this part. Again, please do not get into the the details of it. I'll tell you the flavor of this expression. So what I am trying to say is the gauge field can actually be looked at this form, B inverse some small a plus d of V. So this B is just the R dependent part, and this A is the non-trivial part that was not fixed at all by my gauge fixing condition. So this A has a AU, DU piece and A phi, D phi piece, where AU and A phi both are I probably call this as A, and this I think I call this as B and this as A. So these are the parts of my gauge field which was very much undetermined, and when I said that we need to fix the boundary conditions, that boundary condition is this. For example, this part the part that is coming with, so what did I do? I wrote A as mu A, like this expression. I just expanded it in the basis of my Lie algebra. So here these P's and J's are the Lie algebra generators. So the part that is coming with J and the part that is coming with P is fixed. I mean, I certainly need these combinations, otherwise when I will go to the boundary, I will not get flat space. Should I go back?
You are fixing some boundary condition.
Right, my boundary
yes,
my boundary condition is following, that when I will go to infinity, I should get bondimetric. That is the boundary condition. I mean, bondimetric is the allowed metric at r goes to infinity, from which you can always get asymptotic, I mean, which are asymptotically Minkowski.
And what was the principle for fixing fall-up? So you wanted to fix the fall-up also, right? Not strictly what you get at r.
No, this is so yeah. So this guy is the function of r.
And how did you fix it?
Yes, right, very good. So I would choose it, for example, B. So at this level, Br can be any function of r, and for any function of r, this is a solution. I'll choose this Br as exponential of minus r times any Lie algebra valued parameter. So this just depends on which algebra you are, such that when I am going to large r, this is sufficiently falling.
Very fast.
Very fast, exactly.
Why can't it be polynomial?
Yeah, it can be. You can also take it to be some grass square. Some any Lie, I mean by alpha I mean any Lie algebra valued parameter.
But the charges would it be true that if you take certain follow-up, assume some particular form of for B, and then if you compute the charges associated with these large Gauss transformations, they might not be finite if the follow-up is not fast enough.
Right.
That might dictate that.
Right, exactly. So I would take, so at this level, if I only say that I want things to be sufficiently fall off sufficiently faster, I need to I mean any function that falls off fast is okay, right? But if I choose this to be this quantity, if I choose it to be this quantity, then I can actually show that all the effects from the masses at asymptotic infinity will fall off properly. So that I mean even when I am basically computing their fluxes, it will not give me any non-trivial contribution. So this is the important step, and after that, even after that, I mean my A cannot be completely arbitrary. By that I mean just look at this expression, like this quantity here and this quantity there are related, or I mean if I have a z square here, I actually have a z, if this is quadratic in z square, this is quadratic in z. These are all this p, this j, this z, these are all arbitrary functions of u and phi at this moment. But the combination cannot be generic. If you take generic combination, then you would not be able to get bondimetric at the boundary.
I'm sorry, what is J1, what is J0?
Yes, this guys. So here these ABs are running over 3 values. So these are the generators of my, I mean these are the generators of the Lie algebra. So all I am doing is I am expanding my gauge field in this basis, okay, and then
Okay, so 1, 0 over different components?
right. So 3 components.
So there was a 1, 0 and a minus 1?
Yes, so in this notation this is 1, 2 and 3, but you can write it in L basis where it would, I mean yes, 3 components, that's what is
In the
important.
next transparency, what notation?
Yes, in the next transparencies probably I used 1, 0 and minus 1.
I don't see a minus 1.
Because that cannot come. If I have, okay,
So the condition
yes, minus 1 has to be 0, yes.
Okay, and then the P's also had.
Yes. So P also here had only P0, and so right. So in the AU I had P0, and in A phi I had P0, and in AU I had a P1 and P0.
So P minus 1 again is.
Yes, is not there. So these are the boundary conditions that I was talking about. I mean one needs to, so see, once I have the gauge field, I can solve for it, I can solve the equations of motion, and then I can, from the gauge field I can read off my VLBNs. And once I know the VLBNs, I can actually construct the metric. All I need to make sure is that the metric should look like the boundary metric at infinity.
So this is very different from what we would do. I mean, if we were looking at SU2 gauge theory on a space with a boundary, we would not normally break the SU2 gauge invariants in our boundary conditions. We would say that A phi was 0 or AU was 0 or something like that, but we'd keep the SU2 gauge invariant. We would keep the boundary conditions respecting SU2 symmetry. Here you're breaking your boundary conditions are breaking the whatever, your gauge group. Right?
No, I mean in what sense? So, see, A is completely generic, right?
But your boundary conditions is distinguishing, let's say, J0, J1 from J minus 1, which were all rotated to each other by.
No. He has fixed a gauge.
Yeah, this is a gauge fixed version.
No, but gauge, I see.
Yeah, this is a gauge fixed version. I mean, you can actually choose another gauge also. There is nothing generic about it, but you can choose another gauge such that you go to bondimetric at the boundary.
In fact, one comment, in all of asymptotic symmetry theories, I don't think anybody has very carefully figured out what is the gauge invariant ways of fixing this boundary conditions. In
No.
certain particular gauge people work with it.
Right.
In this case, because this Stern-Simons, maybe you can make more stronger statement. Instead of working in this gauge, if you working in an arbitrary gauge, how things work out.
So, right. So
Yeah, why do you need, I mean, I see.
see, oh, sorry.
If I could,
No, it's
but
okay.
I'm just thinking of normal SU2 gauge theory.
Mm-hmm.
What we say is that the equations of motion or
Right.
one of the equations of motion forces the thing to be pure gauge in the bulk. So it's like U inverse du, and then that part is just pure gauge.
Right.
Only the boundary part matters.
Right.
So we didn't really need in that analysis to fix a gauge in the bulk.
No, but when you didn't choose any particular gauge to, okay,
One can
yeah,
do the SU2 path integral
Okay.
without fixing any particular gauge in the bulk.
right,
That's just working on the boundary.
okay.
Now here you are
So-
somehow.
Okay, so here I have, in fact, if you just. Yeah, here I had already chosen this gauge fixing condition. This is the radial gauge fixing condition, and in that gauge fixing condition, only my solutions looks like this.
Right. So, but your theory is defined by the boundary conditions. Your gauge is your choice, but
Yes.
it's defined by the boundary conditions.
Right.
So you may have stated your boundary conditions in a particular gauge, but I should be able to read off what those boundary conditions mean in some gauge invariant language.
That would be, but this is not wrong. I mean, this you can do.
Yeah.
That is
No,
more
no.
elegant. That is true.
But I just want to know whether that way of reading it off preserves the
Should.
ISO 2,1. I can't see that.
No, I mean, I do not think that the people, I mean, even for ADS,
Yeah, but it may not.
at least
I just
Heno's,
say,
yeah,
you know,
Heno's way of computing was also always like this, that you choose a particular gauge.
Yeah, but it may be physically different because in SU2 the boundary is just the boundary. Here what we're thinking of as the boundary is the part
Yeah,
in the color space.
yeah,
Because it's time.
right,
The translation is
Right.
part of your gauge.
right,
So
exactly.
it may be physically different.
And also like the way we choose these, the boundary conditions on R, on this function B is such that you can choose your boundary to be any constant R equal to R naught hypersurface. That can be any constant R equal to R naught hypersurface, and hence you can as well choose it to be your infinity. As R goes to infinity, and can you do your calculation with this choice. So that is also another thing that goes into choosing this boundary condition.
Yeah, another way of saying it is that the boundary clearly doesn't have the full symmetry.
Yes, no,
But you
it
want to
has.
talk about the translation part or SU2 part? I thought you were talking
Both, the whole IS, wherever, everything.
the
in
whole part.
The whole part.
No, but boundary has that.
Well, boundary doesn't have all the translations, right? Because the boundary breaks.
Definitely. So the other part, the translation part would have something probably.
But even the SO2, 1, right?
The
Boundary
rotation.
some space in that. It's a two-dimensional space.
So I just want to add, I just want to add one thing here is that out of my BMS3, I can get out the entire Poincare algebra. I mean, that is just a sub-algebra of that.
Right, but I'm sorry, we could go on.
No, that's okay.
I'm making
It's
a
fine.
stupid distinction, but the distinction is this, that in the definition of the theory, you're specifying some boundary conditions. And those boundary conditions either do or do not, break down your gauge symmetry in some way. And as I said, when we normally work with an SU2 Chern-Simons theory, we don't break that gauge symmetry.
Okay.
Okay, but here I think you are.
Yes,
And
I
think
mean, I
you're
have to
doing it
choose this, yeah.
intentionally,
Yeah.
And it's sort of interesting, right?
This is exactly the part why translations is important. I was asking you, right?
Right.
The fact that how translations emerge from even at finite.
It's not just translations, even boosts. will
Boost,
move your
yeah,
surface.
right.
So
Yeah, some part.
this is very important.
Yeah.
Yeah, I mean, and in fact, choosing this, again, I would say that this is one possible way to choose it. You can choose it in alternate way also, but you have to choose it. That statement doesn't change.
And did we define asymptotic symmetries as symmetries which will preserve your boundary conditions? Which will preserve the.
I am not,
the follow-up?
right, I am not yet at the level of asymptotic symmetries. Right now, I am just choosing my boundary condition. After this, so here I have just chosen, what have I done? all I have done is I have written down this theory. Now instead of A, I have written it down instead of some other fields, that is it. And all I am doing is I can write down the equation of motion, and to solve it I need a boundary condition. All I have said is I am choosing this boundary condition. I am not yet at the level of asymptotic symmetry. Now I will go to that. So the second step was to find the symmetry isometry transformations that will not change this. Okay. So that's where, so in this case for Chern-Simons this would be just gauge symmetries. So all I will be doing is I will be looking for proper gauge transformation parameters. I can start with the most generic one, and then I will demand that the gauge transformations, which is this equation, will not affect this fall off, and that will tell me what lambda I should have. And once I know the lambda, from that I can construct the corresponding charges, and from the charges I can construct the algebra.
That group is the
Complete BMS3 group.
Okay, so but while constructing this solution, you've already imposed some gauge.
I have only imposed the asymptotic boundary condition, that when I will go to boundary, see there are two things. First is finding solution such that when I am going to the to whatever limit I am interested in, I am getting the solution that I want to get. So here the statement is I want to get my boundary metric at the boundary, and that is how I have chosen my boundary condition.
Yeah.
So
Just
sure, go ahead please.
I'm saying there is no gauge condition imposed yet.
No, this is already a gauge fixed solution.
Okay.
But even after, so this is a gauge fixed solutions which has the property that when I am going to the boundary, it will give me boundary metric. Now I want to understand what kind of gauge transformations are still allowed in my symmetry such that this will not be changed. And those residual gauge symmetry transformations corresponding charges is going to give me the charges of my symmetry.
So what was our gauge fixing again? I mean, just to remind me.
So here I first chose yeah, right. So I first chose del phi of AR equal to 0, and then I chose this BR, these guys, as some exponential of minus r times a number. This number depends on like what group you are working with. By that I mean, am I doing pure gravity or supergravity or high spin gravity, whatever, the r dependence does not change. This thing can change. Yeah, I'm sorry. I mean, these are like, yeah, I should have been spending more time, but like. Sure, please.
So this BMS3, which is the symmetry group of the boundary, right? Is that of
Yes.
that is of the boundary?
Right.
And that contains the Poincare algebra.
Yes.
So, but it seems that this kind of translation would be broken.
But translation would have a okay. So what would be your translation? If you are in the bulk, your translation is like any x mu going to x mu plus some a mu, will be your translation. Now when you are in the boundary, you have u and phi. So here you have two distinct kind of transformations. One is a transformation that is just changing any function of phi by like a phi dependent. What I mean is phi going to any function of phi, and u going to u plus some other function of phi. So these guys are like, now you can just expand them, right, in exponential in the circle basis, and you will have infinite number of them. Just finite number of them will still give you the corresponding transformation, but you cannot really map it to that. You do not have the information about the third.
Is it the same relation with the EDS-CFT where this is conformal isometry versus isometry? Is there some sense in which
Yes,
is a conformal
right.
isometry?
I think so. Yes, you can get the yes at least. Yeah. Yes. Right. True. Okay. So that is the idea. So from here you basically then find out the residual gauge transformations that is not going to affect this fall off, and that would give you the finally from that, once you have constructed that lambda, not constructed, once you have found that gauge transformations, you can find the corresponding conserved charge, and then from there you can find the algebra. Okay, like technically a bit difficult. I mean, of course, like if you have many matter particles, it is difficult, but at least at the level of understanding it is clear that this is what one has to do to get the symmetry algebra. So here like yeah, I mean, what I wanted to say at the last line is like once I break down, once I explicitly find the modes of these fields, of these independent fields, you will have infinite number of such modes, and hence of course the algebra that you will generate from here would be an infinite dimensional algebra.
And all this we have to do because there are infinitely many supersymmetric completions or supersymmetric versions of an infinite dimensional algebra which contains BMS as a bosonic set. And you have to
Yes,
narrow
of
it
course.
down.
Right. I mean, bosonic just okay. The bosonic part would certainly be there. I mean, if I would have started with ISO 2,1, I would have gotten BMS3. If I instead of that, if I am starting is n equal to 2,0 super point carry, I will again get BMS3 and the extra parts of it. So all of them will have BMS3 as its subgroup, and the other generators will have the
So there are many, like infinitely
many.
many supersymmetric.
Not infinitely many.
Not infinitely.
I mean,
multiple.
yeah, n equal to 2, 4, 8. If you are if you are saying that I only want to close the algebra linearly, but if you allow like non-linear closure, then you can have any number of n possible. Yeah. And that can actually, I mean, what I am trying to say is one can actually get those symmetry algebras by doing this asymptotic analysis of the corresponding gravity theory.
Corresponding gravity theory.
By that I mean I will start with a supergravity theory where I would allow the supersymmetry algebra to have the quadratic coupling. Yeah, not so super. I mean, if you are saying that I want to write down a supergravity theory where the supersymmetric algebra will close linearly, then you can only have at max n equal 8 number of supercharges. You cannot have more than that, and the corresponding R symmetry would be AC2. But if you allow non-quadratic completions as well, I mean, so what I mean is.
So that would mean even the parent algebra is funny, or
Parent algebra itself is any n. Parent algebra itself can have any n. You don't have to restrict to any quadratic. Yes, yes. No, so I mean that a.
what is non-linear algebra?
Yeah. So that's what I wanted to write. So it's we should not be calling them algebra. So for algebra, like if I have two generators, I should just get the right hand side. I should just get one, right? But by those kind of things, I can actually get like JCJ. I mean, they can close quadratically as well.
But let's say in the parent algebra, the Virasoro completion, I mean, it's the super Virasoro thing.
Right.
I think it is a standard thing.
Right.
N equals to 2, 0 or 2, whatever, right? And then I look for various contractions such that the boson, as a bosonic subgroup, I have BMS3.
Yes.
And there are multiple ways of
Right.
BMS3.
Right. Right.
And there you could also get non-linear things.
Right.
Even when the parent algebra doesn't have this.
No.
Okay.
You always need the parent algebra to has that property to get it. So if your parent algebra does not have this kind of a coupling, your daughter algebra won't have it. I mean, not daughter. I mean, they are like infinite dimensional. They won't have.
What for the second lower line?
This kind of thing.
What is any example?
I think I cannot tell you, but I can give you the reference. This is again by a paper by Heno, Liat Maus. Yeah, that paper has this. This is called inextended asymptotically ADS algebras, and they are yeah. Yeah, I understand. I mean, maybe at this point, you might think like, okay, fine. I mean, you know it works for BMS. If you work hard, it will certainly work for super BMS and everything. So what is a big deal? It is not really a big deal in that sense, but just give me some time because I want to tell you how much time do I have, by the way? 35 minutes. That's long. Okay, good. Okay, so let me go ahead then. And so in this case, the case that I was talking about, if you do the finish your calculation, then what you get is this as your symmetry algebra, and you can see that the first line is already the BMS, the original bosonic symmetry algebra, the BMS3, and then extra whatever you have is because of your matter constraint. So that's it. Now, what more can we understand? So I'll not go to the details, but I'll tell you like what more data of your theory you can get by doing this analysis. These are following, that once the asymptotic algebra is constructed, first thing that you can understand is what would be the energy bound of any classical states for their theory that can be obtained. then a generic solution that would satisfy this appropriate energy bound can be computed. Further, the amount of supersymmetry that your solution will be preserving can be understood. And then finally, you can actually get, like we actually found all sort of purely bosonic topological solutions in these theories, and they all are different and distinct from your Bondi metric. Of course, they are distinct from Minkowski metric. They are also distinct from Bondi metric in the bulk, but they all are same when you are going to the boundary. And these solutions are cosmological in nature, so they will have a cosmological horizon, and their thermodynamic properties can also be computed. So this is exactly in the line of understanding BTZ for ADS. So that the entire procedure actually works here, and you do get all the zero modes. These solutions are the BMS zero modes that you were talking about. You can construct all of them. I mean, you can in principle construct all of them. In practice, of course, I do not have all the solutions because not possible analytically, but there are infinite number of possible solutions that you can get. I have only constructed some of them which are like easy to construct, but one can do that. So these are the zero modes that you were talking about. So all the BMS zero modes can be computed.
What are the solutions? What are the zero modes? You have the solutions in flat space and you have their analog. Some of them you have the analog in ADS.
Huh? Sorry, repeat your statement.
So in flat space, right?
Yes, yes.
And you said that you know what are the soft modes in flat space, and then you have identified them in ADS3 also?
No. That's not what I said. I said this construction is in the same line of understanding the BTZ black hole solutions and its thermodynamics for ADS3 theories. And all I was trying to say that Heno has done it probably maybe 20-25 years back, but that was for ADS3. Here, by using the similar kind of technique, you can understand the solutions and the zero modes for flat space gravity. Okay, that's what I wanted to say.
In ADS, if you took just plain ADS, then you get all these boundary gravitons around ADS, right? You get the Virasoro multiple.
Right.
But then, in addition, there's this genuinely new solution, which is the BTZ black hole.
Yes.
Here, presumably you have the analog of the boundary gravitons.
Yes.
Is there any analog of the BTZ black hole?
The solutions that here I am talking about, they are not same as Bondi metric. So they are not the usual things that we are talking about.
So
these are the analogs of.
What are these solutions? What are they're not black holes?
No.
So what
They are cosmological in nature. So they are not black hole solutions. These are like you can have this point like conical singular solutions, and I mean but they will, you need to impose the energy conditions, and you need to, that's all that you need actually. So if you impose the energy conditions, you can find number of possible solutions. And
if anything happens in 3 dimensions, at spatial infinity it gives rise to a log.
At spatial infinity, sorry?
There's a log.
Yes.
That is allowed by your boundary conditions? I'm asking.
I have not, so here the boundary conditions are only at null infinity.
I
Yes.
understand. That's
Right.
why I'm asking, it's okay with you if at spatial infinity there are logs?
Right.
These are all okay solutions?
Right.
Okay. And now, I'm trying to understand, you're saying that cosmological means things are, what does it mean that the solutions are cosmological?
So that it will have a horizon kind of a structure, but it is not a black hole horizon.
It will have a horizon. What will the Penrose diagram look like, for instance?
Can I show you the solution?
Sure.
Is it? Can I do it just after the talk?
Sure.
Okay. Yeah, I'll show you the solutions. I mean, I'll show you how distinct they are. Okay. So okay. So let me tell you, like, so far what we have obtained. What we have obtained is following: that Chern-Simons formulation of 3D gravity can be understood, and we can use this to get the asymptotic symmetry structure at null infinity. New bosonic solutions can be obtained that has a different topology than the Minkowski spacetime, and they are dynamical solutions. This is important. So these are dynamical solutions of a two-dimensional theory that lives at the boundary of, the 3D manifold, whatever manifold you are looking at. So yeah, this will live on U phi hypersurface. Yeah, right. So then it brings us to a question that can we find the boundary theory?
Sorry, Nabamita, these In Strominger's story, there was scry plus, there was scry minus, and then they were sort of tied together by something else.
Yeah, I not.
Special infinity. Do you have the analog of that? I mean, this log worries me. It looks singular. I mean, roughly, I had the intuition that pure gravity in ADS3 was well defined, but pure gravity in flat space, three-dimensional, was more singular. And you're telling me that's not true. I just want to.
I mean, you are asking me that would I have a log term in the solution or not?
I think you will have to have a log term at infinity, at spatial infinity, right? Just the Coulomb law's log.
At the spatial, so you are asking me, like, although you have a solution at scry plus, can you take that limit?
Yeah, can
where
you make it smooth this way? Yeah. You agree that just the fact that the Coulomb law is log tells you that, you put something in, it changes what's happening far away, some important.
But is conical singular solutions?
Just borderline, anti-borderline, right?
Yeah, but you should be able to sew them up.
Yeah, I mean that was
The limit of this is the limit of that.
that was somehow by hand in Strominger's paper. Just a second.
Having a log is like, we will discard the solution.
I don't know. It just feels singular. She will know.
Yeah, I will tell you. Okay, I mean just give me some time. Let me finish it. Yeah. So what the next question that I want to understand is, can we somehow get our hand to a two-dimensional theory whose solutions these guys would be? Okay. So if we can, we have to see at till what level can we really call it dual to 3D gravity. Again, we need to understand what would this duality mean, because so far all we have done is classical, right? I mean, so duality we need to define precisely in what sense it would be dual. And what I want to tell you is, like, in whatever time I have, is we will exploit the equivalence of again Chern-Simons theory and Wess-Zumino-Witten models to show that there are two-dimensional theories whose solutions these guys are. Okay. And then again we can understand some part of it, at least the thermodynamics aspects of it, its symmetries, its global and gauge symmetries using, I mean, in terms of the 2D theory, but till now nothing more than that. I mean, okay, let me get there. Yeah. Okay, so just 2 more minutes to understand how the CS and Wess-Zumino-Witten equivalence works. Probably again many of you know. So this Wess-Zumino-Witten model is nothing but a two-dimensional nonlinear sigma model coupled to a three-dimensional term of this form, where the small g's are just the extensions of capital G's. So capital G's are defined on a manifold, and small g's are just its its mirror or whatever, its extension to the boundary, or rather it's better to say that capital G's are extensions of small g to the bulk. So of course, you can do it in multiple possible ways, and there where the arbitrariness comes in this, and that one has to do properly. So in the theory has conserved currents, and that actually gives you a conserved current algebra, and from the current algebra you can construct the corresponding stress tensor which is responsible for this corresponding symmetries. So this is a very quick way to say what Wess-Zumino-Witten is, and what I can tell you is that again here the important data that you need to keep in mind are the boundary conditions. So we have seen that in the Chern-Simons theory, since our manifold is very specified, so we need to impose, we have already imposed certain boundary conditions on the gauge field, and these boundary conditions on A basically means constraints in the phase space, and so we need to identify the conditions, and then so that this does not bringing any to make our classical action well defined, we need to add the boundary terms as well to our Chern-Simons action, and then that combination can actually be shown equivalent to this Wess-Zumino-Witten model thing.
For gauge group ISO2.
Yes.
And this boundary in Chern-Simons, if you have, let's say, on a cylinder, if you want to do it in a cylinder,
Yes.
then these boundary terms are certain fixed terms, fixed by the fact
Right.
that you want your equation something well defined.
Right.
But I would have imagined if I am doing this analysis, these boundary terms do not play any role if you are doing this earlier part. In the earlier part, you ignore this boundary term completely. Right?
No, of course, I mean, I ignored these boundary terms completely, because as you will see that they will not really have anything non-trivial in the dynamics. But right now what I am trying to show is I am trying to show that the two actions are same. So Wess-Zumino-Witten action is not really, it's not really a two-dimensional action. You see, there is a three-dimensional part, but just let me. But the dynamics of this entire theory lives in 2D.
Yes.
Yes. Now you
so,
tell me.
so if I think about it, that I have a three-dimensional bulk in which I have Chern-Simons, then on the boundary of the three-dimensional bulk, I have a boundary contribution, which is this,
Right.
and they together make up this WGW model.
Right.
In the earlier part of the talk, you analyze this bulk Chern-Simons term quite carefully, and
Bulk chance, yeah, I mean Chern-Simon action, yes.
Chern-Simons action,
I basically actually looked at the solution of the Chern-Simon theory, which was,
all of them are entirely from the bulk perspective.
yes, but the non-triviality,
Came from the
arbitrariness was only in the boundary.
So the fact that we need to consider this boundary at chi plus or chi minus, if I add this boundary term, let's say I want to make Chern-Simons theory well defined. If you inside this Penrose diagram, then would you say presumably you will need some boundary term?
Right. Right.
So then that boundary term might also say something about the algebra.
But they will not give me anything to the dynamics.
They will not give me anything to the local dynamics, but from the perspective of boundary.
I mean, I won't be able to define the variation properly if I do not add this boundary terms.
Sure. And they do not do anything to the previous system.
Right.
This is only.
Right. I mean, all you can show is the solution that I showed you will actually come out to be the solution of this theory. But to write down the equation of motion of this, and I mean, okay, what I want to do, I want to show that the solution that I had is a solution of a two-dimensional theory. To get to that two-dimensional theory, I need to add this, because I see, okay, again, these two are same only on shell.
These two are at this level, they are equivalent at the on shell, but this duality can be made off shell as well. The Chern-Simons
Yes.
already
Yes,
but
yes.
let's talk about on cell.
Right.
Even on cell, when you are evaluating charges, let's say I have Chern-Simons plus boundary term, and I want to evaluate charge for a global.
Absolutely, we will do that.
Large gas
You will do that,
There
exactly.
There will be a contribution to this from this S Chern-Simons.
No.
S Chern-Simons, the local.
Yes, Chern-Simon, of course, yes.
Your point is that the second one does not contribute.
Right. And I'll actually show, I'll construct this, I'll write down its symmetries, I'll construct the charges, and I'll show that this is exactly the BMS3 that we obtained. Okay?
So this is the chiral Wesson-Witten algebra?
Yes.
And is the claim that these two theories at classical level are just identical?
Yes.
That your bulk theory with these boundary conditions is chiral Wesson-Witten algebra with this case group?
Right.
So
At classical level.
everything I was saying at the beginning was wrong.
What?
Because you're not breaking the.
That is what I thought.
Even after gauge fixing the.
Because that was, I could have chosen it in any other gauge, but I had to choose it. That's what I know.
Okay. Thank you.
So, yeah, you can skip this. This is basically to tell you like what should be that boundary term. This is the boundary term, and this is the total action that one has to take. And then finally, this comes out to be the Wesson-Witten model that we need to look at. So, this is this is a chiral Wesson-Witten model that Shiraz already, I mean, yeah, a two-dimensional theory which is also known as chiral Wesson-Witten model, and the dynamics of the solutions that we were talking about is governed by this. Okay, one can get to this, yes.
Prime is in the phi direction and dot is in the u direction.
Right. Yes, right. Sorry.
Why asymptotic? I thought it's IISER to come over.
Good question. Is it my mistake?
It's my previous.
Is it? Yeah.
That would be the ADS thing, right? No, that would be
Yeah, I mean, okay. This will have the same symmetry as that. I should write it as IISER 2,1. The names, I mean, for me, what is important is this will have the same symmetry as the theory that I started with.
No, but is it 6-dimensional group or 3-dimensional? I
3-dimensional. No?
but your original, yeah, ISO was 6-dimensional.
So you are okay. You are asking me like what are the generators of this, right?
How many? To start with.
Yeah. Let's go there. So okay,
I mean, to me, it's very important whether you're
I'll
breaking
have.
or not.
I'm not breaking.
But it looks like, if you're saying SL2R, it looks like you're breaking, right? Because you started with a 6-dimensional thing and you're ending up with 3-dimensional.
there's no IISER to come over. Would be asymptotic. Yeah, like you said, so it could be thought of that way.
No, I can show you that I'll still have 6 generators. I'll have a symmetry algebra for this. Can I, let me look at this.
Whatever it is, but the gauge, the Weissman-Witten theory is based on a gauge group, which is SL2R.
Oh. Oh.
If you did the same thing for SU2 in the normal way, if you started with the SU2 gauge theory, you would end up with an SU2 Weissman-Witten.
So these SL2R generators have the J's, no P's.
So these are like just give me a minute. So this theory, the theory that I have shown here, would have a gauge symmetry as well as a global symmetry. The global symmetry of it will give me a current algebra that will finally give me the entire BMS3. So that will have everything in it. But this theory is also a gauge theory. So like I mean, to really get to the phase space, I need to do a constant analysis that one can do.
Wait, but it's chiral Weissman-Witten algebra based on some gauge group.
Right.
And that gauge group is SL2R.
Right.
Okay, so at least at that algebraic level, there's some breaking going on, it looks to me. Because you started with the gauge theory with 6 generators, you ended up with the Weissman-Witten theory with 3 generators.
But is okay. Is
that right?
Right. But that is because like it. So this is already a gauge fixed version of the theory, no? So it should. I would expect it to be.
I don't quite understand. I mean, chiral Weissman-Witten theory with this is a well-defined statement.
Right. So no, what I'm trying to say is I started with a Chern-Simons on ISO 2,1.
Yeah.
I gauge fixed it, and the gauge fixed version of that gauge fixed on-shell version of that theory with the boundary term boils down to this. So of course I would expect that some part of the gauge symmetry would be broken.
I just go back to SU2. When you start with SU2 in the bulk, you end up with SU2 in the bulk. I mean, that's the usual story. Right?
But that there you do not. So there your boundary conditions are also gauge invariant. That's what you said.
Yeah, that's what I'm saying. I'm saying that somehow you're choosing non-gauge invariant boundary conditions. That's how it's.
Non-gauge invariant boundary conditions.
It's fine, right? I mean.
Yeah, no. I'm just.
The boundary conditions break part of your. Okay, I mean that's okay. It doesn't sound unnatural to me because part of your gauge group is translations, and going to infinity means.
I'm choosing a particular direction.
Doesn't sound unnatural.
I thought in your previous analysis when you had a gauge field version of the gauge field, you could, by doing analysis there, you could recover the whole symmetry.
So I could recover the. No, I could even here that should be true. I could recover the whole symmetry. By that I mean that when I'll go to the asymptotic symmetry, it will have the bulk symmetry as a subgroup of it. But the realization of it would be very different. This is what Abhijit was asking. The realization of it is very different, but it still has that subgroup.
Yeah, we can distinguish two questions. We can distinguish questions with asymptotic symmetries and what the boundary theory is.
Right.
The boundary theory
Is a gauge fixed version. Yeah.
is less, right?
Right.
Than you would expect.
Is a gauge theory and gauge symmetries does not have any particular meaning as long even as global symmetries.
No, wait, but there's no gauge symmetry. It's just Weissman-Witten. Boundary theory has no gauge. I mean, unless I'm misunderstanding. In SU2, you just get ordinary Weissman-Witten theory with nothing gauged.
You don't
Here
get
it
gauge,
is
you
gauged.
Get
get standard
Because Weissman-Witten, there's no gauge. Everything you see is what you.
Here it is gauged.
What is gauge?
Yeah, I'll show you.
Okay.
Yeah. So here all I have shown you so far is if I start with Chern-Simons and then I gauge fix my solution and find the Chern-Simons action on this solution, then I'll get this. Okay, this action will have the same symmetries at. So this is a Weissman-Witten model. I can write down the current algebra. I mean it has certain global symmetries. From the global symmetries, I can write down the current algebras. Am I going? I mean, I'm going too fast. Okay. And from the current, from the generators of the current algebra, I can construct the corresponding stress tensor, and with the stress tensor, one can write down the symmetry algebra. Okay. The symmetry algebra of the stress tensor and the other currents will actually give me the exactly same BMS3. This is statement 1, and now I'll answer Shiraz. Sorry, you had a question? Sorry?
Is it a coset then? ISO 2,1/?
Yeah, I do not know that, but I'll tell you like what further needs to be done.
But this global symmetry that you have, how
Yes.
much you will do Sugara, this global symmetry is what? Is it SL2R?
No,
Oh, what is the global symmetry?
No.
That you have.
The global symmetry, no. The global symmetry would be the same for this theory n equal to 2 comma 0 super point kare.
This is the global symmetry.
Yes,
It's the same global symmetry that you had in the above.
right. Okay. So this theory will have a global symmetry which is n equal to 2 comma 0 super point kare, and then from that you can construct the Sugawara construction and can get the entire BMS.
Sorry, Nabamita,
Huh.
I'm being stupid, but I'm not.
No, please
Once
ask.
you say SL2R, chiral SL2R Vesuvino-Witten theory,
Hmm.
the theory is completely well specified, right?
She's
No.
not saying that.
You're not saying that. What
She's
are
saying
you
chiral W0 model with gauge group SL2R.
SL2R, yes. So it has a gauge symmetry.
Numerator is not there in that statement yet.
It's not there in that statement.
I do not know this language well, but I can tell you what this is. So this is the sorry.
Yeah.
This is the theory that has certain global symmetry and certain gauge symmetry. This theory,
Thank you.
It's not the standard chiral W0 model. It must be, right? Otherwise, how these global symmetries are claimed to be?
what? It's not.
Can you just finish
Not-
that statement?
not this.
You started a statement. Can you
Yeah. So what I'm trying to say is, let me write it down. So I started with Chance-Simon. I add the proper boundary term and I evaluate it on the gauge fixed solutions. Of course, my gauge fixed solution already had arbitrariness in it. So those are the fields which are living on the boundary, and the resultant theory that I get is this, whatever is my I. Okay. This is a chiral Vesuvino-Witten model which has n equal to 2 comma 0 super point kare as current algebra and SL2 comma R as gauge symmetry.
Now I understand what you mean. So it's a coset. It's just a coset of the thing by SL2R. So that is the new thing, the coset. Thank you.
So, fine.
And
So,
this is claimed to be the theory dual to.
dual means, yeah, classically yes, but we still, what we are trying to understand right now, like if we can study some more properties, like some entanglement properties of various states of my theory in this, but I still do not have a concrete answer to that.
But then there is an actual proposal for even the quantum gravity in IISER, where you would say it's a coset of something divided by some.
Is
Terrace
those things are true even for non-compact gauge groups also?
Yeah, I mean, you also have non-compact stuff here, right?
We have, yeah.
So even for compact things, yeah.
But your statement is that it's a gauged Vesuvino-Witten model. The gauging is just to get my model. It's a gauged Vesuvino-Witten model where the gauging part is SL2R. So this SL2R is at all not important. I have a parent theory. This is the gauge part. Whatever left is the actual theory, which is this n equal to 2 comma 0.
No,
The parent theory was the n equals to.
Yeah.
What is the gauged Vesuvino-Witten? What is the starting model and what
So,
is the coset?
so the statement is following. See, let's just go a little.
Understanding SL2R as a coset.
Let's.
Yes.
I think you're holding on by.
Yes. What is the thing that you are modeling off by?
Yes, so let's just go a little bit slow, okay? So what are we doing? So what we have seen is, first of all, we need to put a boundary condition on my gauge fields, right? To get, so boundary conditions on my, let me just, okay. So the entire Chance-Simon gauge field is something like this. This is just derivative operator B, and this is the non-trivial part. So we need to put boundary condition on A. This is very important. Until unless you put the suitable boundary condition, you wouldn't get your space-time to be asymptotically flat, statement 1, and statement 2 you cannot get BMS algebra. Both of them important. Now when I am writing this, there are two steps. So here the boundary condition on A actually, so if you remember, this A had two pieces, one is AU du and another is A phi d phi. The boundary, if you look at them carefully, they are special in two ways. First is U component of A is also related to some part of the phi component of A. I will show you the gauge field end. This is one condition, and second condition is the U component of, sorry, the phi component of A is also special, is also restricted. Okay, let me just show you the gauge field so that you understand what I am talking about. This. See, for example, you can see that this piece, the coefficient of P0 and coefficient of J0 are exactly same. They have to be, otherwise you won't get what you are trying to get. And second is, even here, as Shiraz pointed out, there is no J minus 1. Even in A phi, there is no J minus 1, just an example, and it's special. So it's certainly not the most generic field that one can write down. So both these conditions are important, and then when we will write down the corresponding two-dimensional theory here, okay, when we are writing this down, at this step, only thing that I have used is how the U components and phi components are related. For example, U and phi component of VLVN and spin connection are related like this, and other U components of various fields is 0. This is what has been used to get to this. So this is partially gauge fixed in that sense. Okay, but now to get to the dynamical solutions that I was talking about, which corresponds to BMS3, we need to further restrict it. So that restriction will come, but at this level itself there is certain restrictions that has gone in. Once you put further restrictions to it, you will really get the flat gravity that we are talking about, and that once you restrict it further, you will basically get Liouville, but that is the second step. Yeah.
And how many free boundary functions were there in your gauge field? If you go back to that.
Here, I can, so here you can see lambda, A, anything which is a function of U and phi are free.
Okay.
So 1, 2, 3, 4, 5 and 6, and they are like spinors and scalars and vectors like that.
Sorry, if we just get rid of all the supersymmetry and so on, just the bosonic.
Right, let us just look. So for bosonic part you will only look at lambda and B. So you have capital lambda and small v. So this is free and this F is free. So from here, yeah, okay.
So only 2.
Yes.
Sorry, this K was what again? This is the Newton constant, related to Newton constant?
Yes. This will be related to, this is the level of chance happen which will be 1 over 4g finally. Yeah.
But if the claim that CC is making that the symmetry is the same, then why is you breaking?
No, it looks like my breaking is wrong, but it looks like the reduction is right somehow. But I had expected the number of free functions to be 3, because 6 minus 3 was 3. I don't understand the 2, so I'm understanding something wrong. But somehow it's.
The number of free functions just for pure gravity would be lambda and F, just 2.
Which is 2. So I thought you were going to start with IS whatever.
And 3 of them is broken by the choice?
No, and then in the end I just want to look at the final boundary description. So if the claim is that it's some Weissenstein-Witten theory based on a 6-dimensional gauge group, modeled out by a 3-dimensional gauge group, then there should be 3 free functions.
Yes.
But that's not what, that's somehow not understanding. But why don't you please go on?
Yeah, I'm trying to think that. But basically these are the fields that are finally going to, I mean their modes are finally going to give me the ISO 2, 1, and there I only have J's and P's. So why should I have more than that?
J's and P's 6 things.
Right. So here also, of course, you are right. So here also I'll mode expand them, and I'll have actually infinite number of them, and just the 3 of them will give me the bulk algebra.
Now the phase space of the, we're trying to identify the
Phase space.
of the bulk theory
Right.
with the phase space of some boundary theory. The phase space of the bulk theory you showed us from the first analysis, right?
Right.
The set of all free functions in your gauge fields.
Right.
So here you're telling me that is 2, right?
Right.
Right? I could count that when you said it's 2.
Yeah, this is lambda and F. These are the 2 things.
One further.
Sure.
The transparency where you should one more. The one that we kept looking at, the form of the gauge field. That one.
Yes.
There.
Yes.
Here, how many free functions?
P for the system that you are interested in, P and J.
P and J.
Yes.
Fine. P and J, but the Z?
No, no. So you don't want to, you only want to look at pure gravity, right?
Yeah, pure
Yeah. So for you only P and J.
P and J. Okay,
Right.
good. So there is a system with two free functions.
Right.
Now you are saying that this can be recovered by some boundary theory.
Right.
So the boundary theory in question, whatever it is, has to have a phase space with two free functions.
Two free functions. Yes. And that's what is my lambda and F.
Yes, but I'm not understanding what the description of the boundary theory is. If the boundary theory is a coset of a 6-dimensional thing by a 3-dimensional thing, I would have expected 3 free functions. So it's kind of, so I'm not understanding that. So I'm trying to understand what is the boundary description that gives you this space.
The boundary description is this. If you let's just not look at this statement, but this is correct.
Okay. The boundary description is that. Now, can
Yes.
fine,
Now,
I'll ask you. Please.
no, 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 no.
But I want to translate this into something I can understand. Is this a Wechsler-Witten theory?
Yes.
Some gauge group,
So-
some group?
Okay, when you say okay, let me just get, because that would be. So here this is what is your Wechsler-Witten of the group is G is that group element?
Yeah, both that del G and that G.
Right.
Both of them belong to some group.
Right.
G?
Right.
Yeah, so which group does that belong to?
It would be n equal to 2, 0 superpoint.
So let's throw away the supersymmetry. Is that ISO? Whatever?
Yes.
Okay. Then that has 6. If it's just that,
Right.
it has 6 free functions. So
Right.
it's not identified.
Right. ISO 2, 0, but now it is partially gauge fixed.
Partially gauge fixed,
Yes.
which means that there is some breaking of that or not. Okay, fine. So you're doing something. You're taking this Wechsler-Witten theory, which is a phase space with 6 free functions,
Right.
and you're throwing away 4 of them somehow.
Right. Because I am eventually I will only have lambda and F. Yes.
Okay, and I want to understand how you're throwing away those 4. I mean, just group theoretically,
Oh.
if that's possible.
I mean, you want to understand it as a from. I mean, the symmetry group of this theory. Yeah.
Right. If I was clever enough, I would online try to understand those formulas. I can't do that.
No.
I'm just trying to get
No.
it
That's okay. Oh, so what? Okay. Let me. I don't. From group theoretic perspective, you want.
from
to.
any assist.
Yeah. From my.
structural.
So you
From
say where is SL2R? You say SL2R. What in this line?
Yeah, that's a good question. So let me just try to understand that. So SL2R would mean okay. So this this system will have some further gauge invariance. So the theory that I am writing here is it has global symmetries as well as certain gauge symmetries. That residual gauge symmetries would be SL2R.
So would you write in the can you go to the Wechsler action?
This is the Wechsler.
No, I mean the standard form with the
Yes,
D. Yeah.
yes.
So there, would you gauge it by making that D the covariant derivative with respect to
Right.
And that you are saying is SL2R.
Right.
So that's the standard gauge WCW coset.
Okay.
Okay, where you
So
have
that is what.
some local symmetry in the numerator and the denominator is what the A lives in.
That gauge fixed version is the Liouville version of the theory. Yeah. I mean, okay. Yes. One has to do that also.
So,
Yes.
so now I guess the question partially is the 6 divided by minus 3, 6 minus 3.
So where is okay?
So it must be more than this gauge, right? To get rid of one more. So it's something else.
Something else means yes, because so at this level itself we have lambda and F, but what one needs to put is further constraints. So that cannot of course increase the number of degree of freedom. You think it should be more than 2, right?
I mean, the words ISO gauged by SL2R. I'm not sure I understand why this SL2R lives in the ISO, but whatever. These words would suggest a three free function phase space.
If this statement is true.
Yes.
So far what she has done, she has fixed the gauge. That fixing already breaks some of the gauge transforms. Only some of them are left. And then she had some very specific boundary condition that also breaks something. And then she is left with 2. I don't understand exactly how she left with 2, but this is the statement.
No, but even earlier we were only 2 fields, right? That P and J, which was the non-trivial fields of my theory.
Yeah, so that's great. The bulk analysis is totally clear. You have 2 free fields. Now I thought the idea was that you would get an independent boundary description
Right.
that would give you the same 2 fields.
Right.
You've given an action
Right.
boundary action, which
Right.
is great.
And it also has two fields. That is
It
also
also has
correct.
two fields.
Right.
And I just want to understand what the connection of that
With-
standard Wessumino is.
Isn't the standard Wessumino-Witten also let's just forget about all this bunch. The first line and this term, is it not the standard Wessumino-Witten? It is.
As long as lambda belongs to some group.
Of course.
Okay, good. So what group does it belong to?
So I am telling you that this capital lambda certainly belongs to n equal to 2 comma 1 super point current.
Which in this case is
Oh yeah, sorry. IISER 2 comma 1.
Okay,
Yeah.
so that's now, there will be a 6 function phase space of this theory.
Right.
Then you gauge that, you say by some SL2R.
Okay.
As Abhijit asked, where in this slide is there an SL2R?
So just a second. So here, if I look at this theory completely, then I certainly need the information of small lambda as well as capital lambda into it. I am just trying to do the counting. So small lambda in it will have lambda and zeta, and capital lambda in it has lambda and zeta, and B in it has E and F, but still it gives me only 4.
Yeah, but then by saying that it has only 4, you're saying that little lambda is not just an arbitrary SL2 ISO element, right? Because that would have 6 functions.
Right.
So it's not.
Wait. Now, these are all matrix valued functions. Does that solve your problem?
Yes, probably.
These are all matrix valued. So there is a trace involved. These are all matrix valued functions.
Up there, those lambdas.
Those are all matrix valued functions.
Where in your boundary conditions,
Right.
those were genuine functions, right? Just plain functions.
Right. Sorry, just a second.
You've written on lambda something,
Here?
Yeah, those P and Z.
Right. Oh,
Those were just normal functions.
right.
So
How am I going from? Oh. Okay. So from here, now I understand your question. So from here, you will first construct the current. Okay, I'll give you the expression. For example, for just pure bosonic theory, by the time in like ISO 2 comma 1, you will have two currents. So one of them will look like lambda inverse lambda prime. This is one current. Let me give it this name J, and traced of course. And you will have another current, let me call that P, that would involve lambda inverse F lambda, again traced. These are the currents. From here I will construct the bilinears. Let me just write down the bilinear for you. It is like JJ plus, and the other one is
I want to understand what's the
PP.
boundary description that gives you the same phase space.
So these are the J, and what was my notation? Some M and P, right? So M and P. These are the two M and P that I was talking about. So you have to take the trace over that. So these are all matrix valued functions, and these matrix this is the for this case it should be ISO 2 comma 1.
Okay, so the phase space of your boundary description, this lambda, there are, if I count in ordinary functions, there are 6 chiral functions as part of the phase space. How does that go down to 2?
How does that go down to 2? Okay, so here these are certainly like at this level these are all matrix valued fields. Okay.
And therefore 6 real functions.
Right. So I mean you are asking me like how to construct those currents, right, from this?
I want to know how these two systems are equivalent. If the claim is that these are equivalent as classical theories, they should have the same, the phase space of the boundary theory should match the phase space of the bulk theory. But one has 2 functions, the other one, now I'm understanding, 6 functions. You know, but maybe we could continue over lunch now. You could finish up and.
I mean I'm almost done.
So just one question. This whatever this
I mean, if I write it, so you are, sorry. By that you mean, I mean, by holomorphic fields you are means like if there will be only, no, they are functions of u and phi both. Yeah, they are functions of u and phi both and not a particular combination of it at this level. Just a second. So one has to further gauge fix this, but I am still little bit confused, like how many.
Here what is happening, say you start with the group but you are not looking at arbitrary configurations of your gauge field. You have some very specific boundary conditions, and those boundary conditions are changing the effective degrees of freedom even from the bulk analysis. So you start with some gauge groups, you put some boundary condition which is breaking it to some, let's say H, G to H. Now for that H, this description should match with that H. The boundary description, which is entirely in terms of boundary, should have this H, same number of parameters as H.
Is each a group or a coset, or is there a residue description?
Right, so now what is H? This is the question you are asking.
Yeah, the H can actually be written down. So I'm trying to show you.
Even the beginning question is also interesting. Why G is broken down to H? Why is this boundary condition important? What is that?
The boundary condition is important to get the.
Why do I need to get BMS? I mean, sorry, you see, I have to ask logic.
Yeah, but we can postpone those questions till lunch, right? Now let's just
Yeah.
understand the answer.
Yeah, I mean, here the prime motivation is to get BMS. So that is a separate question. I mean, you were asking me why have you chosen that boundary condition? That is because I was interested in getting. I mean, my prior motivation was to get this. Now to answer, Shiraz, let me just.
Probably very stupid question.
No, just wait. No, it's not. So just give me a minute. So I'll just write down lambda. From lambda, I'll define 3 fields. Oof, I mean, it's like complicated. I'm just trying to understand like how with little bit of equations I can tell you the data. So to begin with, I'll have a certain number of scalar fields. Just a second. Actually 6, as you rightly said. And then once I will impose the further boundary conditions, I'll have the reduced action will actually have only 2 fields. In fact, it would be a Liouville theory consisting of 2 fields. Yes. So the thing is like, yeah. So the thing is like here at this level we have lambda and if. So forget about the other fields because those are coming from the supersymmetries. If I am just looking at ISO 2,1, my boundary theory will have information of lambda and if. Even when you will evaluate these terms on these solutions, it will only depend, these other pieces will fall down. Sigma and you will not be there and you will have information about lambda and if. These 2 in total contains like total 6 datas, and then one needs to remember that we have to impose other conditions as well. So far we have only imposed how the u component of the gauge field was related to the phi component of the gauge field, but the phi component of the gauge field was itself constraint. So once one imposes those constraints, then finally the degrees of freedom of the theory reduces to 2, which is out of the 6, 2 combinations of the fields will survive, and that's what, yeah, and that theory would finally be the Liouville
So
theory.
some constrained subspace
Yes.
of a Wesso-Winovich theory.
Yes, we will have the dynamics of P and J that we have talked about.
Okay. And this constrained subspace, does it have the full symmetry?
By full symmetry again you mean like
ISO or whatever.
yes, it will have. The bulk I mean, okay, it will, let me restate, this full constraint subspace will have entire BMS3 as its symmetry and as a subgroup ISO 2,1. Yes.
Okay. Sounds, I need to understand some things, but sounds great.
Yeah, I can show you some of the equations if that helps you.
Yeah.
but I know it won't help you. So yes, you are right, like one has to further after this. So okay, let me tell you by steps like what one needs to do. After one gets this, one can try to understand the symmetries of this theory. First, let us just understand the global symmetries of this theory. The global symmetry will give me a current algebra, but from that current algebra directly one cannot get, I mean this current algebra will not give me BMS. To get BMS, we again need to impose the entire boundary conditions, the constraints coming from the boundary conditions, that will further put constraints on my theory, and that finally will give me BMS. So a constrained version of this theory will have the same symmetry as BMS3. That is the right statement. And another statement is one can write down that theory, that you can finally write down that constraint theory which will have BMS3 as its solution. So it will exactly have two unknown fields, I mean it would be a theory of two fields.
And do you write it down as an action that whose solutions give you that theory, or is it this action plus some set of constraints?
No, I will write it down as an action whose symmetry would be exactly same as BMS3.
And whose equations of motion?
I will have to, exactly, the equation of motion will match with the equations of motion of P and J. Yes, but it is only up to this level that these two theories are identical. So I will say like only classical level that they are identical.
That's right.
Yeah, that one can do.
It sounds very interesting. It sounds very interesting.
So I mean this is like rich, but I do not know offhand like what more one can get from these theories, simply because like there is not, I mean for pure 3D gravity, since there is no dynamical graviton, I do not know like exactly what kind of questions one can ask there. I mean if a question can be formulated in the bulk, its answer can probably be obtained from here, but I do not know what kind of a proper question one can ask there. That's the, yeah, that's the bad part of it. What do you think?
Should we clap first?